Most of these reactions we're going to be doing today, we're going to be doing in these little spot plates. Pretty simple. You're going to put a couple drops of each thing into the spot plate. You're going to see if a reaction occurs, and you guys are going to describe it based on what series you're doing. So kind of walking through it and walking through the chemistry that we're going to have to do. Series A is going to be all about double displacement. So what is a double displacement? A double displacement occurs when you have two compounds reacting with each other. So for this case, for this example, we'll use, let's say, lead nitrate and let's say sodium chloride. So again, if you guys need practice writing out the formulas here and getting the proper subscripts and everything, just remember that all compounds are neutral. So we have to charge balance these. So we know nitrates are 1 minus. And in this case, lead is going to be a 2 plus. So in order to charge balance this, obviously we need 2 of the 1 minus. And 2 times negative 1 is going to be negative 2. Negative 2 plus positive 2 is going to be 0. So this is a neutral compound. Sodium chloride, pretty simple. Sodium's plus 1, chloride's minus 1, plus minus. They balance each other out without the need for subscripts. So again, periodic table is going to be really useful for stuff like this. So if you look in the first column's all plus 1. Second column is going to be all 2 plus. Transition metals are a little wacky. You got some multiple charges there. And towards the far end of the periodic table, the group with fluorine is going to be minus, the group with oxygen is going to be 2 minus, and the group with nitrogen would be 3 minus. Another thing to keep in mind too, I've got this little label here, AQ. All AQ means is aqueous, which means we have a solution of this. The other possible little labels you're going to see are for the 3 phases of matter we'll be dealing with, so either solid, liquid, or gas. And again, that's just going to tell you what exactly you have going on. So how do we go about actually predicting what's going to happen here? Well, remember I said those solubility rules are going to be very important for this experiment. The best way to describe this is we have to switch the partners of these. So remember, we're making ionic compounds, so that's going to be a positive cation and a negative anion. So way you can do this and represent this is if you kind of just exchange these guys, we can see what we'll possibly get. That's not going to tell you if there's a reaction or not. We have to look at what the products will be, and that will determine if a reaction occurred. So if we exchange partners here, we're going to get lead chloride, and we're going to get sodium nitrate. So if we look at our solubility rules, it says all sodium salts are going to be soluble. So this one's going to be soluble. It also says all nitrates are going to be soluble. So this is going to be really soluble. So this is aqueous. And if we look at our solubility rules again, it normally says that chlorides are soluble, except in the presence of a couple of cations. Lead 2 plus is one of them, so this is going to be insoluble, and this is going to be a solid. So since we formed a solid, this is what's going to be known as a precipitate. And since we formed a precipitate, a reaction occurred. If we did all of this and both our products were soluble, let's say, there'd be no reaction. And the best way to see that is through a net ionic equation. So what we wrote here was a molecular equation where you're seeing the formulas for each of these guys kind of written out and everything. The total ionic and the net ionic are going to kind of tell you what's actually going on. Because remember when I said, when I labeled these guys as aqueous, and I said, it just means we have a solution of them? Well, in that solution, we don't actually have sodium chloride existing like this. What we actually have is sodium ions and chloride ions separate. So next step would be, let's write the total ionic equation for this. And basically what we're going to do for total ionic is just break up all these components into their ions. So that would be lead 2 plus NO3 minus plus Na plus Cl minus. That's all going to go to. Now, when we get to this, because this is a solid, this doesn't break up into its components. So this is just going to remain PbCl2. Again, because it's solid. I should technically, after all these, have aqueous, but you guys can get the idea. And then the end of this is going to be plus Na plus NO3 minus. Now, I should point out, too, guys, I didn't bounce this equation up here. You should make sure you always bounce your equations when you're doing stuff like this, because you guys can see this is unbounced. Remember, we can't create or destroy matter. So if we were going to bounce this, the way I bounce equations is I usually just start with one element and just basically keep a checklist on what's on each side. So I go one by one. So lead 1, lead 1. The trick with polyatomics is if you have polyatomics on both sides, so NO3 as a group, NO3 as a group, treating them as one thing, and it makes your accounting a lot easier. So in this case, we have 2 nitrates. We only have 1 nitrate here, so we needed to put a coefficient in front of here, so that's 2. And when I did that, obviously, now we have 2 sodiums on this side. I only have 1 sodium on this side, so if I fill this in, now we have 2 sodiums here, and that makes 2 chlorides. If I go here, I already have 2 chlorides. So now that I've gone through it all once, I kind of just double check, make sure I didn't mess anything up when I put those in. So start again, lead, 2 nitrate, 2 nitrate, 2 sodium, 2 sodium, 2 chloride, 2 chloride. So that's all bounced. And obviously that would transition down to here. So now I have 2 Na plus and 2 Cl minus, and I have 2 Na plus and 2 NO3 minus. So this is the total ionic equation. So to get the net ionic equation is kind of the too long didn't read version of the total ionic. So you look at what was made. So we actually made lead 2 chloride. So we have PbCl2. And then what went into making that? So what went into making this was the lead 2 plus the 2 Cl minus. And obviously this will be solid. These guys would be aqueous. The other thing you can see here is the spectator ions. So the spectator ions are going to be the ions that are the same as they were at the beginning as they are at the end. So you can see we have, this should be a 2 as well. Now everything's officially balanced. So we can see here, 2 NO3, 2 NO3, so we can cross those out. 2 Na, 2 Na. And you guys can see what's left over is everything that went into our net ionic equation. Now, remember when I was saying before that we can really see what was actually occurring in the reaction, or if there was a reaction or not, if we write the total ionic out. So let's say, hypothetically speaking, in a strange, bizarro universe, that this was soluble in solution, and this was aqueous. Now, underlying again, this is not the actual condition. This is just hypothetically speaking. Well, what would happen is we would break these up on this side. We wouldn't keep these as a solid. We would have Pb2 plus and then 2 Cl minus. You guys can see that if we broke those up, well, now 2 Cl minus, 2 Cl minus. Pb should be a 2 plus, Pb2 plus, Pb2 plus. And you guys can see everything would be crossed out. So what we're saying in that case is everything that was at the beginning is the same as it was at the end. If everything is the same at the beginning as it was in the end, nothing happened here. So in that case, we would say no reaction. So that's how you can predict reactions, is something has to occur. You have to have a chemical change happen. So this is all series A. You're going to have some that react to give you precipitates, some that don't. The handout's going to ask you to tell like the color, the precipitate, and everything, just be careful because some of the reactants you're going to be using have a color to the solution. Just because the solution is a color does not mean that precipitate is that color. For Series B, we can almost treat it just like one of these double displacements with an extra step. And that's because one of the products it's made. So Series B is going to have a carbonate reacting with an acid. So let's say we had HCl, aqueous. So guys, for inorganic acids, anytime you see H followed by this, it is going to be an acid of some sort. So HCl is one of our strong acids, so we just treat this as a ionic compound. So an H plus and a Cl minus. So let's say we have this, and we're going to react this with some sodium carbonate. Again, guys, carbonate is a 2 minus, sodium's a +1, so we need 2 of those down there, and that makes that neutral. Hydrogen's a +1, chloride's a -1, so again, that's neutral. So remember, I said we can treat this kind of like a double displacement, and this is solid. So if we treat this like a double displacement, just like above, right, those replace each other, we're going to get NaCl, which is going to be aqueous. Guys, the other thing, too, with the solubility rules, use your everyday experiences and common sense in there. So sodium chloride is also table salt. So if I put table salt in water, it dissolves, so it's soluble. So we get this sodium chloride, and then we also produce this H2CO3. So this guy here is what's known as carbonic acid. So remember I said we can treat this as a double displacement with an extra step. So carbonic acid, and you guys will learn this in Gen Chem 2 most likely, doesn't like to exist in solution like this. So what actually happens is you get what's called an equilibrium that occurs. So what you get is basically this wants to convert to another thing, and that other thing also wants to convert back to this. But you're going to see it's going to be a special case with this, which is why this basically just disappears on us. So it's in equilibrium, and it's in equilibrium with water and CO2. For the biologists in the class, this is a carbonic acid equilibrium. It's a component of your blood buffer system, so you can actually relate respiration with blood pH, and there's a lot of cool biochem problems you can do with that. Hey guys, sorry for the kind of abrupt cut here. I just wanted to clarify this a little bit. I didn't like how it came out in the first take, so I'm just going to kind of redo it real quick right here. So we're just talking about the carbonic acid equilibrium. So it was H2CO3 in equilibrium with CO2 and H2O. Again, kind of like I said, don't worry too much if you don't get this now. You guys are going to learn this properly in Gen Chem 2. But when we have equilibriums occurring, we have to use a principle known as Le Chatelier's principle. And Le Chatelier's, you can think of it kind of like a bounce. When you change things on either side of the equilibrium, the reaction is going to respond to try to maintain bounce. In this case for us, we have our CO2 here, which is going to be a gas. Well, we're not capturing that gas. We're going to let that gas bubble off. So we're going to remove some of the CO2. So what's going to happen with that, when we remove CO2, the equilibrium is going to respond by shifting to the right. It's going to shift to the products here. So it's going to take this carbonic acid that we formed, and it's going to convert it into CO2 and water. That CO2 is going to keep leaving, resulting in more of the carbonic acid wanting to convert to CO2. So you guys can see, by constantly removing this out of solution, we are going to convert basically all of this into CO2 and H2O. So in the end, what our reaction would be HCl plus Na2CO3 goes to, now we're not going to write this because it's just going to convert all into this, so we're going to get CO2 as a gas plus H2O as a liquid, and our sodium chloride as an aqueous salt. So now for Series D, and yes, I know we went A, B, D. Series C we cut out for time purposes from the normal lab. So Series D is what's called single replacement reactions, or another way to think of them is oxidation reduction reactions. Now, these are personally some of my favorite demos to do. They work really well for demos, but basically they're just like the double displacements we did, except one of the reactants is going to be an element. So in this case, let's say we had some zinc metal, so zinc solid, and we're going to react it just like you guys do in this experiment with some HCl, which is going to be aqueous. Well, again, if we treat this just like the double displacements, except now one's an element, this is going to go swap out with that. We're going to get zinc chloride and H2 gas. And obviously if we bounce that like that, so zinc 1, 2H, H2, 2Cl, 2Cl, so everything's balanced, and this is going to be aqueous. So unlike the double displacements where I said, you're going to look to see what forms on this side in order to predict this, the way you predict these single displacement reactions is by looking at something that's called an activity series. If you guys look in your textbook, there is probably an activity series. Always just double check, because you can see activity series that read from top to bottom or bottom to top. So just make sure it'll tell you which one will displace the other. You're just going to read the fine print of each of them. And basically, if you have it in a setup like this, let's say, the zinc's going to pop off the H plus in here. You're going to get zinc chloride and H2 gas. This is fun because, as some of you know, this guy's flammable. So you can capture this gas in a balloon, let's say, and you can ignite a balloon of this to prove that it is hydrogen, which is actually a really cool demo to do. So the net ionics in this one, guys, it's a redox reaction. So it's a little difficult to do because the description I gave you for the double displacement kind of breaks down when you're trying to do a net ionic for this. You have to follow the electrons in this. And if you guys haven't got to redox chem yet, don't worry too much. I'll kind of show you the overall way we can do this real quick. There's some general rules. If you've got an element by itself, its oxidation state is what we call 0. So these two are going to be 0. And then in this case, the two metals that are in the compounds are just going to be their charge. So this is going to be plus, and this is going to be 2 plus. So if you guys keep in mind that electrons are negatively charged, if we just look at each of these consistently, so if we look at the zincs versus the zincs, so if we look at this, guys, so we have zinc 0 to zinc 2 plus. Now, if we think of this, how did this zinc become 2 plus? Well, it also lost 2 of its electrons, right? So electrons are negatively charged. The other way to think of this is we have to charge balance this. So zinc's neutral here, zinc's 2 plus here, so we need 2 electrons on top of that to balance that out. So guys, if you see lowercase e minus, that's just shorthand for an electron. And the opposite here would be true. So in this case, we have a H plus an electron, and we're going to get hydrogen by itself. Now remember here, we actually had H2, because hydrogen is what we call a diatomic. So in this case, this was actually just, 2 and 2. You guys can see these electrons kind of cancel out each other. So these would kind of be the net ionic equations for this series here. The last thing to keep in mind in this reaction is the oxidation and reduction portion. So just in case you guys haven't learned it, one of the ways you can remember what's oxidation and what's reduction is just by remembering this little phrase, Leo. Ger. So what this stands for is less electrons means oxidation, greater electrons means reduction. So in that case, if we look at our little example problem here, we saw that the zinc went from 0 to 2 plus. Again, remembering that electrons are negatively charged. If we went from a 0 charge to a 2 plus charge, we lost 2 negative charges, or in this case, we lost 2 electrons. So the zinc was oxidized in this case. So zinc went from neutral to 2 plus 2 electrons, so it lost those 2 electrons. So we say that the zinc was oxidized. The hydrogen in this case went from a +1 to 0. So if we go from +1 to 0, again, electrons are negatively charged. We gained a negative charge, so we gained an electron. So the hydrogen was reduced in this case. Now for Series E is all about acids and bases. And thankfully for you guys, the net ionic equation for all acid-base reactions, strong acid-base reactions, are the same. So acid-base, remember I said earlier, if we kind of see this H leading something like HCl, that would be an acid. You can also have H2SO4, you can have HBr, HI, and there's a couple others. There's HNO3. These are all strong acids. So, if I react HCl, or any acid, with a strong base, so for you guys, a base is just going to be one of these soluble salts that has this OH group, this hydroxyl group on it. So these two come together. Again, just like before, treat this like a double displacement, so, exchange those real quick. What we get is NaCl, aqueous, and we're going to get H2O. Now, if the H2O wasn't apparent to you guys, the other way you can write this out to see this is if you write H2O as HOH. Because now you can see, that hydrogen came from here, the OH came from here, and you just kind of simplify it back down to that. So the H2O is going to be liquid, obviously. We said that was aqueous, this is aqueous, and this is aqueous. So what actually formed here? Well, what formed was the water. So H2O. And what went into making them? Well, the H plus from the acid plus the OH minus from the base in this case. And obviously these guys are going to be aqueous. So what you guys are going to be doing here is you're going to be adding an indicator into the solution, basically just measuring the pH. So indicators are chemicals that don't interfere with this reaction here. They just kind of report back to us and tell us the pH based on a color change. So you guys are going to be using something that's called universal indicator. And there's going to be a bunch of different colors for different pHs. And basically you're going to keep adding the base to it, checking the color against a little card that's going to be in the fume hood itself, and then just writing what the pH is and just knowing this is the reaction that's occurring. The only other thing to keep in mind is if you look at the reagents for Series E, you have HCl, H2SO4, HNO3. So those all make sense. They have this H here as their acidic proton. The last one, if we look on the sheet, is CH3COOH. So guys, this is acetic acid. It's an organic acid, and organic compounds like to be difficult, and the acidic hydrogen on this one is this guy here. So when this one makes a salt, this is the hydrogen that comes off to form the water. This is what gets left over to make the salt. So if we were doing it in this case, the salt we would make would be sodium CH3COO. So this is acetic acid. You guys, for the most part, should all have experience with this acid in one form or another because acetic acid is the main component of vinegar. And by main component, I mean that it makes up about 5% of the solution, but that's what gives vinegar its taste. So again, same thing, just remember it's this proton here we have to worry about. Other than that, that is it for the most part for the Prelab. I know there's a lot of chemistry to this, guys, so if you have to go back and rewatch the video, please feel free to go do it. If you have any questions, please reach out to me, reach out to your TA. We'll more than gladly go over this